Hello all, welcome to my channel. I'm back with another video. In this video, we will be going through one of the important aspects of deploying Airflow at a large scale. And this I am sharing because I have seen a very large scale Airflow installations which scale to more than 12,000 DAGs and more than 60,000 tasks that gets executed at a particular time. So let's get started. So before we understand what we have to do to create a large scale deployment of Airflow, just a disclaimer: this can be done in different ways. This is an opinionated view that I have seen, and it's generally it may not be a requirement or may not be the right approach for most of many of the teams. This only makes sense if you have centralized Airflow installation where you have many people or all the DAGs or all the airflows, DAGs or workflows getting run from one centralized place. If it's very well accepted solution to have decentralized approach where it might happen that each of the OUs have their own Airflow installation or you have installation based on workspace. Like for example, there is a company called Astronomer that gives you an option of launching as many workspaces you want, and each workspace gets a different Airflow installation that also is centralized and that can run on a single Kubernetes cluster in everything running in isolation. So that is also a valid approach. The things that I want to emphasize in this video is related to the things that we need to scale or we need to have pay attention to when we are creating a Airflow installation for a large scale. So at a very basic level, there are five major operations in Airflow that we have to take care of. One is DAG parsing, which is nothing but whatever folders, files we have in the DAG folder, or if we are using DAG bundles, that also whatever DAG we have in there, that needs to be parsed for the task and that needs to be serialized into DB. So that is one particular task. Then we have task scheduling, which is the job of the scheduler, which does it reads all the tasks which have met the dependency and they have their schedule is arrived. So that task needs to be scheduled so that it can be executed. So that job is of scheduler. Then we have different types of task trackings, like we have sensors and we have deferrable operators that we can leverage to track whether the task is succeeded or task is not succeeded, whether it is running, not running. Then we have web server, which does the serving of the APIs. So for example, if someone wants to know what is the current status of the DAG, they can go to the web UI or the API request can be made and we can get the status and everything. And then we have the DB actually, which does the state persistence. So that's DB is the central, I will say, place or very critical place or component for an Airflow installation. So based on these processes, we can see there are different ways for them to be making scalable. For example, we can have a scalable scheduler, we can have scalable tasks that we run, we have scalable triggers. Trigger is a new approach which is linked to deferrable operator. So I already have a video on deferrable operators. Go see that video. And then we have DAG processor and web server. So these individually can be scaled, and that's where we will be seeing what are the things that we can do to scale these. So first thing is having multiple DAG processors. So what do we mean by multiple DAG processor is like when we have a centralized folder, let's say Airflow DAGs configuration in the config file, if we have mentioned the DAG folder, all the files are parsed in a sequential fashion. If we have only one scheduler, then it will start from the, let's say, from the beginning, and then it will process one file, then it will persist that in DB, then again it will pick up the new file, persist it. So it will have to do a lot of, let's say if we have more than 12,000 or 10,000 or even greater than 500 as well. So it will have to do that parsing, and this parsing happens at an frequency which is configurable, but it takes time, and that's why we have concept of running multiple DAG processors. So what will happen? So we have a configuration called DAG processor dot enabled, and then we say DAG processor dot replicas. If we set it to, let's say, higher number, let's say we set it to 2 or 3. So what will happen now that there will be 3 different instances of DAG processor running, and each will in parallel they will read the DAG directory, and from the DAG directory they can process, they can do the parsing of the DAGs and then can process. So there are two approaches here. One is having each DAG processor looking at one single folder. So what will happen is once, let's say the DAG processor one picks up file number one or DAG number one, it will try to pass it, and while doing that it will acquire a lock so that the DAG processor 2 will not read that file, it will read some other file, and that way the works gets divided. So that is one approach. The second approach is where instead of running this DAG processors running on same directory, we can create directory 1, DAG directory 2, DAG directory 3, and each of these processor will only process files which are present inside that. So that way, if we are running multiple DAG processors and we have multiple different directories linked to that, so that way we can distribute the work even further, and that makes the DAG parsing very quick, and that whenever we make a change, the change will appear very fast. So that is one option that we have, and in this case we have different options. For example, we have, let's say if we have DAG uh, uh, getting placed in a GitHub repository. So one approach is we can use git sync to do the sync of those files, and then we have this DAG processor we are saying enabled, and we are having two replicas for HA. So both of them will be parsing the same folder, and then they will create the tasks based on the required log. They will distribute the work. But let's say if we want to have extra DAG processor as this one where we have multiple DAG processor instead of running one single DAG processor with this is one approach where we have one single DAG processor running two replicas for HA mode, but this is adding more and more DAG processor, and here we can provide a subdirectory which is saying that okay, instead of all of these replicas talking to the same directory, we have separate directory for each of the DAG processor. So for example, we can have this approach where we have one DAG centralized DAG processor which reads everything which is there is coming from either from the DAG bundles or git sync, and then we have different folders, different processors which are processing files for different subdirectories. For example, if we can separate the DAGs based on the OU, and then we can say that OU one gets a or team one gets a for subdirectory named team A, and there is another subdirectory called team B, and there's two DAG processor, which is extra DAG processors, that can continue parsing this. So this is one approach, one other approach where we can do what we call parallelized DAG parsing. Then we have multiple schedulers for HA. So scheduler, as we mentioned, has a work of distributing the or scheduling the tasks and making it available. So we can create multiple schedulers using this scheduler replicas and number of runs that we want for a particular scheduler. So this decides how frequently GES2 will be parsing. And again, this uses the same approach. Like once the DAG parser has persisted the data serialized into the DAG, the scheduler will look at the DAGs, acquire the log, and then execute the or schedule the tasks that are there. So if we have multiple tasks that needs to be scheduled, this distribution of workloads helps in making the scheduler fast. And in case of failure as well, if one of the scheduler fails, the other one can still keep on working and make the task go in. So there will be slight delay, or we may face some zombie works as well, but zombie tasks as well. But in general, for the scalability, this multiple scheduler is a good option that we have. Then we have web servers. This is a no-brainer because Airflow web servers are anyway stateless, so we can create as many replicas as we want, and then we can serve those replicas. We can serve all the API requests using these replicas. So that gets the load gets distributed across multiple instances. Then I was talking about that trigger, which is for the default scheduler, sorry, a deferrable operator. So we have to enable explicitly. So we have to say trigger enabled, then we say how many triggers we want and what will be the trigger capacity. So what basically this trigger that is, as I mentioned that in the deferrable video, if you have not seen, go see that. But just a summary that what happens in a normal scenario where we have a sensor or we have a task that is a long running task, it will acquire the worker slot for all the time, but actual work is not being done on that particular executor or a pod. It might be running on some remote cluster, for example, Spark Submit. So once we have done the Spark Submit, let's say in the cluster mode, the pod which sent that command is not needed. It is only needed because we are just checking whether the Spark job successfully submitted or not. We want to keep on checking the status. But if the Spark job takes a lot of time, let's say it is running for more than 70 minutes, 80 minutes, 90 minutes, so our one worker slot will be always occupied. and it will keep on polling to see what is the status of that particular Spark job. The better approach is that using this trigger, where what it happens, it will submit the job and then it will hand over the scheduling or poking task, poking the status of this particular Spark job to the trigger service, which runs as a centralized what you call poke mechanism. It runs multiple asynchronous what you call threads, and each thread is responsible for one particular trigger. So once we have or a trigger event to be monitored, so once we hand it over, the trigger will have many trigger threads, and it will just check whether the task is running or completed. If once it is completed, it will hand over the task back to the scheduler, and the scheduler will mark that job as completed. So this helps in freeing up the resources that are there, and it also helps in reducing the number of zombie tasks, because generally zombie tasks comes in Airflow for long running jobs. So that also can be uh, something which can be avoided using this trigger approach. Then comes the database. So database is something which is very, as I mentioned, it is very central. Everything happens on the database in Airflow. Everything, like every state change, every parsing, every scheduler, all has an entry in the DAG database. And this database is, as of last when I check, I think it had somewhere around 18 or 19 tables, different tables for different status, like DAG run, task ID, task runs, scheduling. There are a lot of other information also in the database, and this database is what powers everything. So what we can do is we can enable connection pooling. So uh, instead of using one constant connection approach, we can have a connection pool. If we are using Postgres, we can use PG Bouncer. So while deploying in the Helm chart, we can say PG Bouncer enabled. It will create a PG Bouncer back for us, and then it will route or it will do the connection pooling and everything. And also this, because this database is very critical, we should be running it on what you call distributed and high capacity databases. Like we can choose in case of Amazon, instead of you running it on RDS, we can run this on Aurora, because it makes it highly scalable, and even needed we can create read replicas as well. That's a very good approach where but in Airflow it doesn't make much of a sense, because Airflow is mostly um, a write heavy application rather than read heavy application. But still we can make a read replica and point all our web servers to serve the traffic from read replica, and only the scheduler writes, and that parser points to the write endpoint. So that way we can have at least distribution of workload and better scalability in terms of that. Then comes executors. So earlier we only had the option of running one executor, either we can choose Celery or Kubernetes executor. Now we have option of choosing multiple, and it should be that we should choose the right tool for the right use case, and hence we should, if we are doing it in, let's say, shared environment, we should enable multiple Kubernetes executors. It doesn't it doesn't take much, often resource wise. Once we have enabled this, we can choose per DAG or per task basis that which executor we want to run that on. For example, if we need environment isolation, we can use Kubernetes executor to run everything in a pod. If we have very short-lived task which comes up very quickly and goes on very quickly, let's say it is something checking some API call, checking some APIs or making some API download, those kind of requests which are time sensitive. So Kubernetes executor will first spin up a pod, then launch the task, and then the API call will be made. So in those cases, Celery executor is a better option, because it already have a warm pool of workers that keeps on running all the time, and we can simply send the task there and execute it and get the results back. And for other distributed systems as well, we have Dask executor which can run on Dask cluster. So that is another executor that we can enable. And in the newer version of Airflow, let's say in Airflow 3, I think 3.1 or 3.0, from 3.0 onwards itself, Edge executor is also there, which allows us to run the tasks in the executor in the stay in a different cluster or different namespace than the Airflow installation. So as of now, what happens is when we start a task, or when a DAG schedules, when a scheduler schedules a task from the DAG, that pod that comes up in the same cluster where the the Airflow installation is happening, in the same namespace as well. So what this allows, the executor allows, edge executor allows is to run this task in a different namespace, plus it also allows us to run this in a different cluster altogether. So what that will allow us to do is, for example, let's say uh, we have GDPR requirement, or we are doing, let's say, some boundaries are there that okay, we cannot have access to a data zone, let's say business zone versus data zone. That kind of scenario is there, so we can now orchestrate those tasks as well using Airflow. So the only the scheduling and task status and everything will be done from Airflow, but the actual task will get launched on the cluster where the data resides, or the computation is needed. So that is another one thing that we can do. So this is one thing that in the Airflow config, we in the core section we can say executors, and we can provide a list of executors that we want to enable for this particular installation, and the first one becomes the default. If no one passes anything, the first executor will be picked. But if someone wants to use a certain executor, so they can pass that uh, in the what you call task basis, like okay, which task that has to be needed. That is another use case. DAG parsing we have already discussed. Like we can use DAG bundle or DAG folders for different things. Then we also have a secret backend. So generally in the large environments, we don't rely on secrets which comes by default with Airflow. We should definitely use a different secret backend. We can use Hasikoff's Vault or any other secret manager. But generally in large installation, if we make AWS calls, it will be costly operation. So it should be better to use some uh, vault which is running on the same Kubernetes cluster rather than making an outside call. But yes, I mean, whatever backend that we decide, we can choose, but we have to just be sure that we are not using the default secrets backend. We should use the secrets backend which is external to the Airflow environment. So the summary wise, we have different options that we can scale for a work Airflow installation to be considered scalable, or to be able to serve large number of DAG or tasks. That web server we can run multiple instances. Scheduler we can run two schedulers in HA mode. Metadata database can be made external with highly available Postgres like Aurora or Cloud Native PG, and we need to add a PG bouncer. Then executor we can choose multiple and create make Kubernetes executor the default, combine it with other executors for multi-executor feature. Then we have DAG sync. We can use Git sync, which is the best approach, I believe. There are other options like mounting volumes or mounting NFS, but that comes with its own challenges. And NFS mount, let's say if we have many tasks coming or many Airflow instances coming, that also becomes something challenging. So it's better to have uh, do it via DAG sync, which is a pull-based model rather than this model. But again, if EFS is a kind of an okay solution, but that is something that has to be tested, and means tested in a sense, check it with your environment and see whether the IO cost that is there with EFS is not that much high. And then secrets, we as I mentioned, we should use a uh, vault or something. And also one thing is very important is to use custom images. That makes life easier for us. So for example, one approach that I have seen, I have implemented in companies, is that I will use different images for different operators. So based on the operator that is coming up, I select the image that should be used, and we provide centralized operator system. For example, let's say we generally have 12 to 13 common operators which are there, like Bash operator, Python operator. Then we have Spark operator, we have some control M operator. So those operators that we have already built an image, and what we do is in the pod mutation hook in the plugin of Airflow, we provide a mutation hook. What it does, it looks at the task identity that okay, this is the task that is coming. So at the runtime, it modifies the image that should be used. Instead of using the default Airflow image, it uses the image that we have custom built for that particular operator, and it just launches that particular image and do the task and then goes away. This makes our lives easier because because we do also develop the operators for the company to use. So it makes our life easier, so that whatever dependency is needed, it's totally isolated, and we don't have to take care of making a bloated image for all the operators that we have. So that's one approach that we have taken. So this was it. If you like this video, and if you uh, think it was helpful, do share and spread the word about the channel. Thanks. Have a nice day.